Alright, for this video we're going to look at other applications for circular motion. We're going to start with a super sweet roller coaster. So let's say our roller coaster starts up here and then it goes through this awesome loop. And we're at the top of the roller coaster. Here's our roller coaster. So if I wanted to draw a free body diagram, I would have the force of gravity trying to pull me down. And it's actually the normal force of the track that is what keeps me moving in a circle. So here it's the normal force that does the centripetal force. So when I'm looking at this equation, let's say my loop has a radius of 20 meters. And I want to find the minimum speed, my velocity, that I have to be traveling at in order to not fall off of the loop. So in order to do this, I already drew my free body diagram. I know the normal force is my centripetal force. So for this, F sub n has to be equal to or greater than the force of gravity, which would make me fall otherwise. So here, the normal force is doing the centripetal motion. It's the track that's keeping me in a circular path. If the track disappeared all of a sudden, my roller coaster would move off in a direction tangent to its current trajectory. So without the normal force of the track, it wouldn't move in a circular pattern. So since the normal force is the centripetal force, I'm going to insert my equation for centripetal force here. So it's going to be mv squared over r is equal to the force of gravity, which is just mg. And like we talked about before, the mass simply cancels out. So in order to solve for the minimum velocity, my radius just goes over here. So v squared equals r times g. Take the square root of both sides. There's my equation. I just plug in my values. The radius was 20 meters times 10. The square root of 200 is 14 meters per second. So my minimum speed would have to be 14 meters per second. If I'm traveling faster than that, that's good, because then all of the stuff will stay in my pockets. If I'm traveling slower than that, they might have to design a new roller coaster. Alright, so let's look at a different scenario. We are on an amusement ride, I'm terrible at drawing, where you are stuck on this wall. And this amusement ride is spinning, and when it starts to spin, the floor drops out. And we have to find out what is the minimum value that it's spinning at its speed so that you don't fall off of the wall. So you're going to be stuck to the wall. We draw a free body diagram for you when you're on the side. Let's say over here. So this guy right here, he's still stuck on the wall. So gravity is always going down, and the normal force on the wall is what moves him in the circular motion. If the wall disappeared, all of a sudden he would move off tangent to his speed. So it is the normal force that pushes him inward. Centripetal force is inward. Inward is life. And gravity wants to pull him down, and it's actually the friction force which keeps him up. So here's my free body diagram. So in the y-plane, as long as he doesn't fall down, the force of gravity is equal to the friction force. And if we expand these equations, force of gravity equals the normal force times mu. And here the normal force is the centripetal force. So F sub n equals F sub c. The normal force is acting as the centripetal force, keeping us in our circular path. So here I insert the equation for centripetal force. So it goes m times g equals mv squared over r. And all of that is times mu. So let's say the mu value over here is 0.7 and my radius was 10 meters. So we'll look to solve with these values. Once again, we're solving for the minimum velocity. What happens to the mass of the guy? Doesn't matter. It cancels out. So we get G times R divided by mu, all under the radical, equals V min. Gravity is still 10. My radius is 10 meters. We said mu was 0.7. I plug all of that together and I get a velocity of 11.95 meters per second. So we can solve for that. Alright, we're going to look at one more setup. Alright, here we have a table that has a hole in the middle, and there's a mass that's swinging around the table. That's M1, and then M2 is hanging. And the force of tension here is what we're going to look at. So for M2, if we were to draw our free body diagram, force of gravity is pulling it down, and the force of tension is what holds it back up. So M1 is on top of the table. So the force of gravity pulls it down. The normal force supports it on the table, and then the force of tension is what causes it to circle around. So we can solve for a lot of different things in terms of the velocity based upon the mass. But over on the top, these two cancel out. So the force of gravity and the normal force, those two are equal. Here, the tension in the string is equal to the force of gravity. And the tension is what keeps us moving in the circular motion. So the tension is the centripetal force. So when solving for the tension, is going to be mv squared over r. And it's important that we keep the masses separate because here they are separate. They're two different masses. So that's m1. And then the force of gravity down here is due to m2 times gravity. So m1 v squared over r equals m2 times g. And we can rearrange this equation however we like in order to solve for any of these variables as long as we can algebra. So those are the three different setups that we can use now using centripetal motion. Remember, inward is life.